topic of survey sampling. Altogether, as we know, there are 40 modules, and towards the end now we are left with 4 modules exclusively on some topics in the area of survey sampling. So, first we will take up some additional thoughts on PPS with and without replacement, and then we will go for some other fascinating topics. The topics are widely studied in the recent literature, and they seem to provoke interesting research questions in the young minds. With this introduction, we will now move on to module number 14, dealing with PPS with and without and follow-up concept. So, in module 14, we have 2 questions, as I said, on PPS with and without replacement. So, let me read out question number 1. Given a hypothetical finite population of 10 units with the following values of an auxiliary size measure 2.00 etc., you have all the 10 values. Draw a sample of size 3 adopting PPS with replacement sampling method and show the formal expression for an unbiased estimator of the population total. Also show an expression for the variance of the estimate and its estimate based on the sample drawn. This is mostly your training on whatever things have been taken up before in the text. Draw a sample of size 3 adopting without replacement sampling, and similarly this time you are told to suggest 2 estimators of the population total. For each estimator, work out an expression for the variance and also suggest a variance. Part C, draw a PPS sample of size 3, work out an estimate, its variance and also the variance estimate based on the chosen sample. So, this exercise really refers to PPS with and without sampling methods and related formation of estimators. To start with, because all the auxiliary size measures, they are like 2.0, 2.05 etc., you can multiply all of them by a suitable multiplier to make sure that you are dealing with only numbers or integers. So, that is why to start with you multiply everything by 100 to make the numbers read like 200, 205, 218 etc., with a total of 2500. Now, you select a 4-digit random number ranging between 0001 to 2500. As usual, you know the standard procedure for consulting a random number table. You could also generate these numbers in the computer, but anyway, these are the numbers obtained by consulting a random number table. These are 2355, 0903, and you know how to translate that into a corresponding number here. So, using the cumulative totals from the left hand side, 2355 corresponds to the unit number 10, next 0903 corresponds to unit number 5, and so on. You can see how the units are coming one by one in your sample. So, for PPS with replacement sample of size 3, you got the first one as 10, next one 5, next one 7, you stop right there. Therefore, the sample is 10, 5, 7 in that order, but we generally represent it as 5, 7, 10 in increasing order of the levels. Now, as you know, the theory says you have to treat yi over pi I as independent unbiased estimators of the population total. Therefore, you simply take their average. So, T hat y is expression number 1, 1 over little n summation yt over pt for all the units in the sample at different positions, because it is with replacement. Even if there is a repeat, you count it as it goes, and this expression 1 tells you it is an unbiased estimate for the population total. I leave it to you as working out the expression for variance and V hat T hat based on the chosen sample. These are all given in the text. There is nothing difficult about it. Since all the selected units are distinct, the same sampled units may serve as PPS without replacement sample of size 3. This time we have been told to suggest 2 estimators. Naturally, you can think of the Hurwitz-Thompson estimator and the Desraj estimator. Hurwitz-Thompson estimator will depend on the computation of pi I and pi ij's. Desraj estimator will depend on the 3 estimators T1, T2, T3, and then taking their average etc. Details are already laid down in the lecture notes, so I can skip it for further computation. Towards derivation of a PPS sample of size 3, we follow the guidelines given in the text. First, we have to verify a sufficient condition. Sufficient condition is pi has to be greater than or equal to every single pi, the normed size measure has to be greater than or equal to this expression, which simplifies to 0.0741. Now, from the text given data, we find that the minimum p value is 0.08, therefore, the condition is satisfied. We can comfortably apply Mizuno scheme and draw a sample of size 3. The scheme says the first unit has to be drawn differently, other 2 units by simple random sampling without replacement. The computational steps have been well explained in the text, so you can take it up, and then you can, once you have the sample, then you can work out the estimates and the detailed things. For a pi-PS sampling design, the first order inclusion probabilities, the very name pi-PS suggests that pi I proportional to pi, therefore, pi I is n times pi. The use of the horizontal estimator is encouraged, because you know how the pi I value is coming. All that you need to work out is pi ij, and that is straightforward. The expressions are straightforward for the estimator, variance and corresponding variance estimator. We need explicit expressions for second order inclusion probabilities as well, but these are given in the text. So, there is nothing difficult about the whole exercise here. Now, let us take up the problem number 2. Note that the population total T y equal to summation y I, it has an alternative representation. Can you pick it up now?
Assume all the second order joint inclusion probabilities are strictly positive. Viewed in terms of observations involving pairs of units, suggest an unbiased estimator for the total different from the Horvitz-Thompson estimator. Work out its form for simple random sampling without replacement sampling design, and comment on your result. Work out its form on PPSWOR sampling design when small n is 2 and 3. Work out its form when the sampling design corresponds to Mizuno sampling scheme for an arbitrary sample size.
Okay. So, let us note once more that the population total, that is a first order representation summation y I. It also has a second order representation involving 2 pairs of observations, T y equal to double summation y I plus y j divided by etc. That suggests that you can also come up with an alternative estimator for the same population total. That is the question number A. Viewed in terms of observations involving in pairs of units, suggest an unbiased estimator. Okay? Can you continue?
We first discussed some general results. Recall that the population total can be estimated by summing over I belonging to S y I over pi I. Likewise, for known non-zero coefficients a1 through a capital N, T of a comma y is equal to summation y I a I, and this is estimated by summation overall sampled units y I a I divided by pi I. Now, by the same token, an unbiased estimator for some function phi of y is summation small phi of y I is given by phi hat y, which equals summing over the sampled units phi of y I divided by pi I.
Yeah. So, as you can see, these are all additive functions. The moment you have an additive function, you can immediately sort out the estimate by dividing by pi I appropriately. You do not really have to worry about the nature of the function phi y I. It could be anything, it could have a very complicated expression, but so long as these are all additive, you have a very simple expression for the estimate. Next.
This can also be generalized to x of y, which equals chi of y, which equals summing over all i's unequal to j, chi of y I y j, in the sense that chi hat y is equal to summing over all sampled units I not equal to j, chi of y I y j divided by pi I j, under the condition that pi I j's are positive for all pairs I j, whenever chi y I y j is non-zero. This condition is also necessary for existence of an unbiased estimate.
Yes, so you can see this time it is an additive function, but every component involves 2 terms y I and y j, two quantities. That is why you need a condition on pi I j strictly positive, and then you divide by pi I j for every pair of unit in the sample. Next.
We now apply these results towards arriving at solutions to the problems in A through D. A. Here chi of y I y j is y I plus y j divided by twice n minus 1. The rest is obvious. For B, use pi I j equals n times n minus 1 divided by capital N times capital N minus 1 and simplify the form of the estimate. Recall expression for pi I j under PPSWOR sampling for n equals 2 and 3, and the rest is just computation in part C. In part D, note that under the Mizuno sampling scheme, pi I is n times pi for each I, 1 through capital N. Sort out pi ij's and simplify the expression as far as practicable.
Yeah, in the whole exercise, the interesting part is part B, under without replacement sampling. Because you know what is pi ij, the moment you simplify, you will end up with y bar. Okay, so no matter how you look at it, you can look at it as summation yi or summation yi plus yj divided to something, or triple summation yi plus yj plus yk divided by something. No matter what you do, because of invariance of the whole sampling design, you can immediately find out that all of these representations lead to simply y bar, small y bar as your estimate. That is very interesting. On the other hand, for PPS or PIPS, the pictures are entirely different. So, with this we conclude. Now, we will take up some question exercises and MCQs. So, in this module, we have tried to recapitulate our understanding about PPS with and without replacement. Basically, we took up two problems regarding implementation of the sampling designs. Also, we talked about application of the Mezino sampling scheme. Then we talked about various estimators based on PPS with and without replacement. And towards the end, we had a tricky problem, namely the same population total can be expressed in terms of second order terms, namely double summation yi plus yj divided by something, and that promotes that you can think of an estimator using the second order inclusion probabilities. It is not only that you use the Hurwitz-Thompson estimator as an estimator of the population total, in the same token you can represent it using the pairs of units, and as a result you can suggest an estimator based on pi ij. Like that, you could have a triple summation yi plus yj plus yk etc., and that would call for estimation by using the third order inclusion probability pi ijk, assuming that the third order probability is positive. Interestingly enough, if you are in the framework of simple random sampling without replacement, no matter how you write this thing, whether as a first order or second order or third order, whatever you do, these are all boiling down to the good old sample mean small y bar. But otherwise, these are interesting exercises, and that is what we took up here. We now look forward to some interesting questions and MCQs regarding these concepts. Okay, let us start with the exercises under this module. The first question refers to PPS with or without replacement sample of size little n. It has already been drawn using the normed size measures P1, P2, P capital N as usual. You have the original size measures x1, x2, xn, then you have developed the normed size measures xi by total x, P1, P2, Pn, and you have used them to draw a sample of size little n, either adopting PPS with replacement or without replacement scheme. So, you know that you have a sample now. Subsequently, it transpired that the population was wrongly identified as one with capital N units, though in principle it had only n star units, n star less than capital N, and these n star units formed a subset of the population of n units to start with, and their labels are already recorded as 1, 2, 3 up to n star. So, what does it say now? You started with capital N, you did everything, now you are told no, it is not up to that part, it is only up to this much n star. So, it is only a subset of the original population units, but luckily for you, these n star are in the beginning 1, 2, 3 up to n star, after that cut, that is the idea. At this stage, it is suggested that discard the sample so drawn and go for fresh selection. Other thing is, check if the selected units conform to the labels not exceeding n star. You have already taken a sample, check if the selected units conform to the labels not exceeding n star, because n star is your limit. Otherwise, go for selection of extra units from the entire population of capital N units, pretending that nothing has happened, no constant is imposed. Now, collect valid sample units till the count is little n. The idea is you continue doing as you have been doing before, but make sure that you only look for units within up to and including capital N star. The moment you got small n of them, stop there. So, these are the two approaches suggested First one is nothing, discard the sample and then go for fresh selection, that anybody can tell. Discuss the validity or otherwise of the procedure mentioned in B. That is the tricky question. Okay? Also explain the procedure to be adopted in case capital N star units in the population are not serially placed as 1, 2, 3 up to N star. You know that there are N star units in the population. You started in a big way with capital N units, but when you look for identifying these N star units, you find that they are no longer in serial numbers on top of that, they are scattered all over the place. But you know that these are the units to be considered for defining the correct population. Then how do you go for this type of sampling, and how do you modify step B and go for validating the sample that you are taking? Okay, very, very tricky. Good question. Can you read the question number 2 now?
A PPSWR or PPSWOR sample of size n has been drawn using the normed size measures P1, P2, and so on to P capital N as usual. Subsequently, it transpired that the population was wrongly identified as one with n units, though in principle it had n star units with n star more than n. And these n units formed a subset of the population of n star units to start with, and their labels were recorded as 1 through n, leaving the remaining n star minus n population units with labels n star plus 1 and so on to n. At this stage, it is suggested that discard the sample so drawn and go for fresh selection. And B, since all the n selected sample units bear labels in the set 1 through n, and these are within the true limits 1 through n star, pretend that these are the units actually selected from the true population. Accept this as a valid sample and go ahead with data analysis. Retain a part of that sample and replace the rest for a fresh selection, exclusively from the remaining part of the population. Discuss the validity or otherwise of the procedures in B and C. Also explain the procedure to be adopted in case capital N units in the subpopulation are not serially placed as 1, 2, and so on to n.
Let us see. So, this time it says you needed to go for a bigger population, but somehow you thought that some units are not contained in the population, you took a subset. You took a subset and over there you made your selection by using the PPS method, whatever it is. But later you realize that no, it is not up to this, it has to extend some more units which are left outside. Now what do I do? The one is very easy, discard the sample and there is no challenge there. Other one says, since all the units have been selected within the limit, you retain them as if nothing has happened, and then you go ahead and do the data analysis. The part C says that retain a part of this sample, all of them are captured here, but ideally want small n, you can think of a proportional break of small n into n and n star minus n. Is that okay? You think of a proportional break of small n into n, capital N and n star minus n in that proportion, a breaking of small n. And then from here you already took little n, you take a subset of them, and from the other part you make a fresh selection from the rest of the population, and then excluding from the remaining part of the population, whatever was excluded you take it. So, you retain a part of the sample originally taken and replace the rest by a fresh selection. And how many do you retain? You apply the proportional allocation formula, some kind of formula, compromise solution. Now, you have to discuss the validity of the procedure, very good. And then also at the end they are saying that how do you estimate also explain the procedure to be adopted in case the units in the subpopulation are not serially placed. So, they are scattered all over the population, but you know that this is not the actual population is bigger. Then how do you go about this thing? Both are very good, interesting questions. Okay? Now, let us take up some MCQs. Please read.
1. For a sample of size small n equals 2, PPSWR sampling is as good as PPSWOR sampling for unbiased estimation of a finite population total. Is this always true? True at times. Depends on the p vector, and none of the above is true. For a sample of size 3, PPSWR sampling is as good as PPSWOR sampling for unbiased estimation of a finite population total. Is this always true? True at times. Depends on the p vector, or none of the above. For a sample of size 3 under the Matsuno sampling scheme, the pi i's are increasing in the pi's. pi ij is more than pi ij dashed whenever pj is more than pj dashed for each I unequal to j unequal to j dashed. Are both of these statements true? B, one is true, but two is not. C, both are true for certain choices of the p vector. And D, none of the above is true.
Let us start with question number 3. According to Mizuno scheme, we know the easy expressions for pi I and pi ij. Once you write them down, because Mizuno sampling scheme refers to, it prompts through pi ps scheme. So, pi I is already proportional to pi. Therefore, answer to question 1 is trivial. Pi I is increasing in pi because it is directly proportional to pi. Pi I equal to n pi as a matter of fact. Okay. The next one, when you do the computation, you can see very easily that I being dummy, j pi j pj greater than pj prime, that implies if and only if statement in fact pi ij is greater than pi ij prime. So, these are easy things to note. Therefore, the answer is both are true, whatever be the p vector. Okay, that is the answer. But the other two are a bit tricky, I mean interesting. Question number 2, you are referring to PPS with replacement sampling and you are referring to PPS without replacement sampling. Do they mean the same in terms of variance? Naturally, if you are talking about unbiased estimation of the finite population total, you apply PPS with replacement sampling estimator and without replacement sampling estimator. Do you expect that the two will have identical performance? That is never true. Okay? And like that, when you are talking about even for a sample of size 2, with replacement and without replacement, they will be different. General perception is without replacement, that will give you 2 units distinct. Therefore, there is more information, quote unquote, more information in without replacement sampling than in with replacement sampling, even for a sample of size 2. Therefore, you do not expect the two to behave equally. Therefore, here also the answer is D, none of the above is true. Okay, so with this we conclude. Now we will move to the next module. Yeah, whenever we talk about sampling taking recourse to auxiliary size measures, we must remember that these size measures are basically all strictly positive and they are all measured in the same scale, and those are the size measures converted immediately into what we call the normed size measures for all estimation purpose. These are the norm size measures that are used. And then we talk about PPS with and without replacement sampling, Mizuno sampling, the implementation method, then the derivation of the estimators. But the interesting part was, if the population has not been well defined, I mean in terms of the listing, if the listing is in some sense incomplete, either it has overshooted or it is undercount, then there could be a problem if it has not been recognized before and if a sample has already been taken. So, towards that we took up some exercises just to understand whether the whole thing should be discarded or there is any way to recover use what has already been done and to recover the damage that has been made. And in that context, the sampling procedures also have to be noted. Another thing was that if there is a difference, there is a fine point of distinction between PPS with and without, mainly from efficiency point of view. We expect without replacement sampling to do better than with replacement sampling. That is the general scenario here. In the next 3 modules, some uncommon non-standard sampling problems will come up in the context of sample survey research.